All right, now I'm going to assume that you ran this code from /home/user local variable byte 00 no cookie. It has to be exactly that, or you won't see the same thing as me, but that's okay. If you stepped through main plus 32, this is what your stack would look like. First, we have the character pointer B, which I intentionally gave the address of A being 8E4, right? Because we always see those ints get the upper 4 bytes. So 8E4, that is exactly the pointer that we have here. So that was so we could reference B of 0 and B of 3, because in so doing, I found that I could get it to generate an LB instruction. But also we see on the stack here that it has chosen to take the arguments into main and store them on the stack. It put the argc, which was 1, assuming that you have no additional command line arguments. Argc is 1, and the char ** argv is right here. So the pointer to a pointer is right here. So if we go up here, that turns out to be pointing at the same place as our frame pointer actually. So that is where our frame pointer pointed on entry into main. We know because our saved frame pointer is right here. So if that is a copy of argv, then that means what we're looking at right now should be argv of 0, the 0th element of, sometimes you can think of argv as a char ** pointer. I typed that because I'm literally too lazy to type the array symbol. It's one less character. But in practice, when you actually dereference a value, you use things like argv0, argv1, and so forth. So anyways, if this is argv of 0, the 0th entry, then it is a pointer to a character array. So if we go and we dereference that, we will see that the argv of 0 is, appropriately by convention, the name of the executable itself, the full path where the executable was launched from. And we can, of course, see this in the debugger as well. If we examined the argv address as a two giant words, two 64-bit values, we would have seen the first argv of 0, and then we would have seen a null terminator for this array. Going to the argv of 0, examining it as a string, then we see this full string here. So what are our takeaways from this stack? Well, first, the frame pointer has been pointing at argv upon entry, and we didn't even realize it this whole time. But also, the compiler, for whatever reason, seems to be storing copies of the arguments onto the stack. And these are literally not even used in this code. This code does not touch argc. This code does not touch argv, but yet, for some reason, the compiler decided to put it there. And the other takeaways from this is that taking that local variable a, taking its address and casting it to a character pointer address, character pointer, and then dereferencing that pointer by accessing b of 0, b of 3, individual bytes out of this integer, our salad bad integer. I haven't made reference to the salad bad joke yet. The salad bad integer, if we grab the byte 0 and the byte 3, that will lead to these load byte assembly instructions. Additionally, because we're returning an int, the RV64I code which we're running is going to use the subw instruction to do integer-sized subtractions when it takes these bytes and turns them into integers and does the subtraction on that. So some new assembly instructions, that much sought after LB, which we were missing amongst the loads in the stores from before, and also we picked up a subw like the addw that we had already seen. It's just a word size register subtraction used by 64-bit code. And on our diagram, that would be subw there and load byte there.